Hello, I'm Bruce Alford from the Lane Community College Energy Management Program. I teach classes in direct digital controls, commercial HVAC controls, and HVAC troubleshooting and retuning. And in those classes we incorporate a lot of activities within this building as a living lab. We do activities and the students learn about how to save energy in commercial buildings by using the equipment that's in this building.
Hi, my name is Josh Manders, and I'm the Director of Creative Strategy here. We're going to take you on a tour that shows some living labs and how we use this LEED Platinum building to teach the community and our students about how the building works and about energy usage.
Now we're going to start looking at our building automation system and our dashboard. So we have access to the dashboard, which will show up on the main floor. This is the beginning of the dashboard. Students can walk in, students or members of the community can walk in, push on this Learn More button, and we go to a page that says the building that teaches. And then we have individual buttons that we can push. So we're able to look at our LEED certification, our passive ventilation. We can look at daylighting. We can look at water conservation. We can look at our green roof. So we can click on any of these individual buttons here and a new screen would pop up. When students log into our front end, this is our BAS system. We can see over here we have multiple buildings. We have all of these buildings on our campus are actually controlled by this automated logic network. Each building has its own standalone network, but they're all kind of linked. So the students actually can look at any of these buildings, and we do that. We most recently studied Building 2, we studied Building 15, and we also study our downtown campus quite often. I'll show you a few things about our downtown campus and give you an idea of some of the things that students do with this BAS system. Now again, I want to point out that the Energy Management Program is part of the Facilities Division. So the Energy Management Program, the academic side, and the Facilities Department, we're all part of one division, so we can all work together. We have access to the control system, but we can't actually change anything, and I think that's a good thing. What the students do is they make recommendations. We send those recommendations off to the Facilities Department, and then the Facilities Department can actually implement a lot of those recommendations. Most recently, this past term, our students evaluated and analyzed and determined that we could save about 300,000 kilowatt hours of electricity, some of that in this building and some of it in Building 2. So it's a real-world examples where we actually studied our buildings and learned about how to save energy, learned about where we could save energy in those buildings, and actually submitted a report to the Facilities Department, and they can implement the changes that we recommended. We're now in a fourth floor classroom. This is a high-performance classroom, as is the entire building. We'll start off with looking at the exterior envelope. The walls are very well insulated, as is the roof. We have a lot of very high insulation levels. Our glazing in this building is high-performance glazing. As we go into the building, we can look over here and we can see that we have some interior walls are concrete block and walls of concrete. This is a feature that you don't see very often in commercial buildings. Most of the time in commercial buildings you see interior walls that are just framed walls. The thermal mass that's associated with the concrete block and the concrete walls, that tends to minimize the temperature swings during the unoccupied period, so that when it comes time to condition the building in the morning, we have to use less energy to bring the building up to temperature because it hasn't dropped down that much in the wintertime. That's pretty good features of our building envelope. Now we'll talk about the lighting. Primarily, we have a lot of daylighting in this classroom. There's a very large skylight that allows a lot of daylight into the classroom. We have baffles that come down below the skylight, and the baffles tend to distribute the daylight to the ends of the classroom. Without the baffles, the daylight factor in the middle of the room would be much higher than the daylight factor at the perimeter of the room. So the baffles tend to distribute the daylight out to the sides. I can tell you, I've been teaching in this classroom for 3 years, and I've only turned the lights on 3 or 4 times during that entire time. Now granted, I don't teach in the evening, but most of my classes are during the daytime, and I rarely turn the lights on. So I don't know much about the lighting system. However, the lighting system is a high-performance lighting system. We have occupancy sensors that will turn the lights off when there's no occupancy in the room. There's an occupancy sensor up here in this corner, and there's another one in the back corner over there. We have lighting controls. There's a section of lighting control panels here where we can select different scenes. We can push certain buttons. We can close the louver at the top to take out the daylighting if we want to show videos in the room. We also have for space conditioning now, I'd like to talk about the HVAC system. What's unique about this building here is that most of the spaces are conditioned. The space cooling and the space heating is provided by radiant panels or radiant floor panels. All of the heating and cooling for this building is through the radiant panels. We provide ventilation air separately, and the ventilation air is tempered from air handling units that are on the roof. And one of the neat features about the air handlers on the roof is that they're variable speed controlled fans. As the need for ventilation increases, the fans will speed up and bring in more ventilation air into the building. If the building is unoccupied, if we have classrooms that don't have very many people in there, the carbon dioxide content is reduced, it's very low, and the dampers in the terminal units tend to close, and the fan slows down and operates at a much slower speed, reducing its energy use. It's a huge energy saving feature by controlling the ventilation fans using carbon dioxide sensors. We have a carbon dioxide sensor over here on the wall next to our temperature sensor. This device right here is our carbon dioxide sensor, and then over here we have our temperature sensor control. So these are the two sensors that actually control the HVAC system for this room. We also have a natural ventilation feature in this building. When conditions are right, if you see we have a green light up here, when the green light is on, what that means is that the conditions outside are favorable for natural ventilation. When we implement the natural ventilation sequence of operations, the exterior windows open up, and then we'll see that there's some doors up above, and then above the doors that are up above, there's a doghouse up there with powered turbines that actually pull air into the building from outside and exhaust the air through the top of the building. And to help increase comfort for the occupants in the space, we also have ceiling fans that we can manually turn on. If we turn on the ceiling fans, you'll see up above here that each classroom has ceiling fans, and by turning on the fans, that tends to provide a lot more air motion, and that air motion can result in a feeling of being about 3 degrees cooler than the actual space temperature in the room. So that helps reduce the energy consumption in the building because we're circulating the air. All right, we're on the rooftop now of our downtown campus, and we're going to look at one of the air handlers that provides ventilation air to the building. This unit here that we're looking at serves the first 3 floors of the east wing. I'll show you some of the interesting features about this air handler and how I'll discuss a little bit about how we integrate this into our curriculum. First, we have our heat recovery wheel. This section is our heat recovery wheel. This wheel can recover about 15 degrees of temperature. So when we're in a heating mode, we can bring in 40-degree outside air and actually preheat that air to about 55 degrees. That acts as a big energy saving feature because it results in less mechanical heating that needs to be provided by the mechanical room. When the heat recovery wheel is not being used during certain outside air conditions, we have bypass dampers that will allow the outside air to go into the building, bypassing the heat recovery wheel, and the exhaust air can leave the building, bypassing the heat recovery wheel. It results in a lower fan static pressure requirement. So this is our heat recovery wheel. This unit is also a dedicated outdoor air system, so it's 100% outside air. We bring in the 100% outside air across the top half, and the exhaust air from the building comes up and goes through the bottom half of the heat recovery wheel. That's our heat recovery wheel. The next section we have here is our damper section. Here's our damper section, and if we need to, here's a Belimo actuator that actually controls the dampers, the gear-driven dampers. The exhaust air comes up from the building on the right side of these dampers, and the outside air goes across the top. So you can see the outside air dampers are open, allowing the supply fan to pull the air from outside, and the exhaust air goes through this path. So you can see these dampers down here are closed. If we want to, we have the capability of taking this, energizing this Belimo actuator, and we can actually mix return air with outside air, and actually we can turn this into a conventional variable air volume system. But right now it's completely a dedicated outdoor air system, a DOAS. We have multiple filter levels here that tend to improve the air quality of the outside air that's being brought into the building. That's our section, the damper section, and then now we have our coil section. So here's where we have, this is kind of boring here. We just have a single coil in here. The equipment down in the mechanical room can provide either chill water or heating water to all of our air handlers. And there's valves in here. There's some Belimo actuators that control the valves. But this is where the heating and cooling is provided for the air handler. We have a supply air fan section, but this is closed up. We generally don't access this. When the equipment is running, there's a lot of high positive pressure that would cause these doors to fly open. So we don't open up the supply fan doors, but there are supply fans behind here that are operating to put the air into the building. Now we come around to the end of the air handler, and we get to our control section, and we can see this is a really great opportunity for the students to study the automated logic control system for the individual air handlers. Here we have an entire large cabinet. I can bring up a whole class here, and we can study this. We can study this control cabinet. As you can see, all of the inputs. These are inputs on this side of the control module. The outputs are on the right-hand side. We have analog outputs. We have digital outputs. We have all of the inputs, and they're all labeled, so that when it comes time to do some troubleshooting, the students can see exactly which wire is attached to which input device and which wire goes to which output device. So this is our main controller. This is hooked into the main building automation system. And students love to come up here and see how everything's wired up. We have miscellaneous devices as well. All of this over here comes with the air handler, but this is the control component right here. And you can see all of the inputs and the outputs. Over here on this side, we have the variable frequency drives. This is the supply fan variable frequency drive. This is the return fan variable frequency drive. And when we study these air handlers, when the students study these air handlers, we can actually look, using our BAS system, we can actually look at all of these points. We have access to what is the speed that the fan is running at, what is the speed that the exhaust fan is running at. We can come over here, we can look at all of these points by looking at our BAS system. The building automation system, we have total access to it. We can look at all of these points, and as we look at these points, it can help us define how the equipment is operating and whether or not it's operating as designed. So this is a really great feature for the students, and we spend a lot of time up here evaluating this equipment. Okay, we're on the south side of the roof right now. I'm going to show you some features about these dog houses. These are primarily used for our natural ventilation feature. Again, when the conditions are right, when the outside air conditions are right, the exterior windows will open up, and then there's doors in the upper levels of the classrooms that will open up, and I'll show you some of those doors as we look inside these dog houses. These panels right here allow the daylight to go into the classroom. So on the 4th floor, you can see the five 4th floor classrooms all have these skylights in the roof, and then so the daylight goes through here, and then it goes into the classroom that's directly below us. The turbines that you see at the top, they are not mechanically powered. Those are powered by very small levels of wind that will rotate those, and what they do during the periods of natural ventilation is as they rotate, they can suck the air out of the building. So with the exterior windows being open, and then the doors being open into the upper level of the classroom, and then these turbines will rotate, and they will actually suck air out of the building as part of our natural ventilation feature. We can actually look inside the doghouse. If we come over on this side, if we look over here, we can actually see the louver that was in the classroom that's directly below us. And you can see these doors. Each classroom has 2 doors, and they're automatically operated. So when the natural ventilation sequence energizes, then these doors open up, the exterior windows open up, and then there's a path for the air to come into this doghouse and then get exhausted out through the wind-powered turbines. If you look over on this side, on the right side of the doghouse, you see another set of doors, and those doors actually exhaust air from the 3rd floor classrooms.
So now we're walking to the south part of the building, and as we get to the end here, you'll see that there are 3 different types of solar panels. Now these solar panels are the type that generate electricity. So from the sun, they're able to gather and harness that and put it into our building. Now there are 3 different types of panels here, and the students are able to compare the performance of each panel type. So over a given year, or over a given day, we're able to see how each panel performs and take that information back into the classroom and see how that impacts our building. So how much energy we're actually generating for the building here.
Okay, we're now in the courtyard between the academic building behind you
and then the residential building on this side. We're going to take a tour of the central plant here, but I wanted to point out that what we have buried under the ground here are two 10,000-gallon tanks that recover rainwater. So most of the rainwater that falls on both of these buildings goes into two 10,000-gallon tanks, and that water is used to flush the urinals and the toilets in the academic building. Unfortunately, in the summertime, if we don't have a lot of rain, those tanks become empty, and then we have to go across the street to the Eugene Library to use the restroom.
And we have a window that we can look into the mechanical space. So it allows students to see some of the mechanical systems that are operating the building. So here we are at the mechanical room. Now this space is where the living labs all come together, in that the space is built for students to learn. As we walk through, you'll notice there's a lot of information presented on digital dials. We have gauges. We have all sorts of different types of equipment. And this all means that students are able to use this space as a living lab and operate within the space comfortably, safely, and have hands-on time with the equipment.
Okay, these are our two condenser water pumps. They're about 20 horsepower each. They're both running right now. These pumps are responsible for circulating water through the condenser water loop, and then also they're allowed, we can open up this valve and we can pump water down into the wells. So these condenser water pumps, they are responsible for pumping the water into the wells. If we need to put heat into the ground or take heat out of the ground, depending on what our space conditioning needs are, we can open up this valve and pump the water into the wells. Over here we have a couple of boilers, and these boilers were actually an afterthought. These are actually part of the educational, the academic system. The energy model says that we don't really need the boilers. The heating load for this building can all be satisfied by the wells, the heat that's actually in the ground. But we decided to put these boilers in as an academic activity so students can actually look at these boilers. We can turn these on. They're high performance boilers, they're hydrotherm boilers, and they're high efficiency, but we don't use them very often because we have very mild weather here in the Pacific Northwest. This device over here is our water-to-water heat pump. This is a device that serves either chilled water or heating water to the air handling units. So if two of the air handlers want heating water, this will generate heating water. What's left over after we send heating water out to the air handlers is that we send the chilled water into the condenser water loop. So this is our water-to-water heat pump. On the other side of the water-to-water heat pump, over here we have a heat recovery chiller. This device over here, this is responsible for this can generate heating water and chill water. So this is the device that can cool half of the building if it's getting a lot of direct sunlight, and it can heat another half of the building. So the building can be zoned. We can generate heating water and chill water at the same time. This is our heat recovery chiller. On the other side of the heat recovery chiller, we have our pumping stations. We have multiple pumps. Because we're using water to transfer energy to the building, we have a lot of pumps. So we have primary and secondary pumps. All the pump piping is labeled so the students can come in here and they can identify specifically which pumps are attached to which system. We have gauges up here. There's individual gauges. Each pump has a gauge, so when a pump is operating, we can look at its suction pressure and its discharge pressure, and the students can do calculations to determine what the approximate flow is and how much energy it takes to generate that flow. Backing up just a little bit, we have two heat exchangers over on this side. During times of high cooling load like today, this equipment here, this heat recovery chiller, is generating chilled water, but it's also generating heating water. So we have to have a place to take the heating water in order to satisfy the load for this chiller. The chilled water goes out to the building and satisfies the cooling load. The heating water would get pumped over to here. The valves would open up, the BAS system would open up valves, and the heating water would go through a heat exchanger over here, and then that heat would eventually get put back into the condenser loop. If the condenser water loop gets too hot, the valves will open up, and that hot water in the condenser loop will be pushed into the ground to be cooled. And then it comes back out of the ground 5 degrees cooler than when it went into the ground. And that's how we reject heat to the ground. Okay, we'll look at our heat recovery chiller now briefly. You notice that the panels have been removed so that the students can actually see what's inside the heat recovery chiller. We have compressors on the top, 6 15-ton compressors. as the refrigeration cycle the students can study, we notice that over on this side is the chill water side. This is the heating water side. Again, this is the heat recovery chiller. It generates both chill water and heating water. On this side of the heat recovery chiller are the evaporators, and on this side are the condensers. So in the vapor compression refrigeration cycle, we have a compressor, we have an evaporator, we have condensers, and then we have thermal expansion valves. And those pieces of equipment operate to make the chill water and the heating water. And the students love to come in here because they can study this, and they really get a feel for how this equipment operates, because they can see how the compressors cycle, and they can also see this is a cold pipe, this is a warm pipe, chill water side, heating water side, and that pretty much takes care of our heat recovery chiller. So on this side of the mechanical room we have our pumping stations. There's each of our pumps has a variable frequency drive that controls it. They're all variable speed pumps. They're also duplex, so 3 of these pumps aren't operating. These 3 are operating. Students come in here, they can record the speed and the amps of individual pumps. With that information, then we go around to the side and we can look at an individual pump. We have our gauges here, and we can measure the suction pressure, and we can measure the discharge pressure. There's the suction pressure of this pump, 25 psi. I close that off, open up this one. The discharge pressure is about 35 psi. The students combine this differential pressure information with the variable speed, the speed of the pump, as well as the amps, and then they go into the classroom and get a pump curve, and they plot some information on a pump curve, and it helps them determine what the flow is and whether or not it's operating at its optimum condition. So this is a really valuable exercise for the students to be able to look at the pressures, the suction pressure and the discharge pressure, record that, and then take it back to the classroom. All right, we're now looking at a graphic for one of the air handlers in our downtown campus building. This is the graphic for air handler 5-01. And the students, as part of our troubleshooting and retuning class, they evaluate how this system is operating. Each student gets an air handling system, and they look at this and they study it. And what else do they study? They study the logic. I'm going to click on a tab called Logic up here. And I won't go through very much of the details, but this is the logic. What this does is this is the actual program that tells that piece of equipment how to operate. So what we do in several of our classes is the students study 3 pieces. We study the graphics, we study the logic, we look at a sequence of operations, which is a document that was designed by the mechanical engineer to tell the piece of equipment how to operate throughout its entire operating cycle. And then the last thing that they do is they look at trends. So this is a trend that somebody else has constructed for this particular air handler, and it just shows some different points. But the trend is valuable because it allows us to see how the equipment is operating. We can construct a trend with all of our points. We have access to create a trend for all the temperature sensors, all of the pressure sensors, all of the VFDs and the speeds. Every point that's on this control system, we can create a trend. And I have the students create trends to confirm whether or not the sequence of operations is being properly implemented. It's a great exercise for the students. It's a real-world application. We find issues where the equipment may not be operating the way it's supposed to, and those are the types of issues that the students write up in a report and submit that to the facilities department. So this is a really great tool here.
So now we're in our computer lab. This is a BAS workstation. The students actually build in 2 of our classes, DDC1 and DDC2. They actually build a mini computer network. We have sensors that are plugged into each controller. We have each workstation will have a controller on it. Each student can put zone sensors on their workstation. We can have switches. We can have temperature sensors. We can have outside air temperature sensors. They all get plugged into a controller. We have a computer fan that is an output for this controller. We have a red light and a green light to simulate different conditions. We have terminal units, terminal blocks for 12 volt DC, 24 volt AC. We have control transformers in here. The students actually build this. The students start with a blank workstation similar to the one that's behind me here, and as each class comes in, they were responsible for building their own workstation. There's a network that goes from workstation to workstation, and then the students can actually program this controller to take the inputs that are on this side, and they can actually construct a program that will turn this fan on, it will turn the red light on and the green light on. It can make the actuator on the back side wave the flag back and forth. And that's all, and the students actually do all that work. And another feature is that we constructed these workstations so that we can open up this, and a lot of the wiring can be done from behind, so that we can expose the wiring. It's important to note also that the students do all of the wiring. They put all of the devices on this workstation, and they're responsible for generating the program that gets uploaded into these individual controllers as well. It's a great project for the students.
So the great thing about this program is it brings together hands-on knowledge into the learning lab. It brings it into the building. So we build stuff here, we strip wire, and then we bring that knowledge into the environment, which is our building here, our living lab. And we're able to take both of those pieces and bring them into the job workplace. So when students graduate, they're able to have a wealth of knowledge, hands-on experience, know their environment, and they're bringing that into their career. So thank you for visiting Lane Community College.